Okay, so last topic in our syllabus it is multi-leaf springs. See, these multi-leaf springs are most widely used in automobiles. You can see this picture also here. This is what we are discussing about. This is what we call it as multi-leaf spring. So, these multi-leaf springs are used as a suspension systems in the automobiles. Now, if you look at this picture here, if you talk about the construction of this one, see, you can see that here there are number of plates. So this is one plate, another plate, like this. You can see there are number of plates are there. They are stacked one upon the other. So that means placing one upon the other, and all these are connected through these things. This is what we call it as a U clips. The clip is in the shape of a U. So then this is U bolt. What you can call it as, this is a bolt which is in the U bolt. Through U bolt, this spring is connected to the axial or automobile, and here you have a pins are there through these pins. So that means the spring is connected in three ways. So one is here, another one is here, maybe other side here also you have, which is not visible in this diagram or in this picture. So this one we call it as eye of the spring. So this side, and similarly have one more eye here also. Two eyes are there. So the eyes are inserted into these pins which are connected to the automobile, and here they fix it to the axle through U bolts. Then we'll call this one as a rebounding clips, which are also in the U shape, but we'll call this as a rebounding clips. So what is the function of this rebounding clips is, this will arrest the movement of or sliding between the two plates here. You can say this is one plate and this is another plate. If these U clips are not there, then what happens is the top leaf will call each plate as a leaf. That's why it is called a multi-leaf springs. You have a multiple number of leaves here. That's why it is called multi-leaf springs. So now when these U clips are not arranged, so there is the possibility of sliding of these leaves one upon the other when the load is acting on this through this connection. So here the main purpose is to carry the load, and at the same time it will provide some amount of suspension to the automobile. So under the load, in our course, what we need to see is what are the stresses acting in this leaf spring when it is subjected to load through this. The load is transferred to the spring through this connection only. So what are various stresses? Of course, here we'll treat this one as a cantilever beam, something like a cantilever beam, because it is fixed here. If I take this portion or this portion, we can treat each portion as a cantilever. So in this cantilever, we'll try to find out what are the stresses. So for that, first we'll discuss about the construction of this leaf spring, then we'll go to the stress analysis part. So the multi-leaf springs are widely used for the suspension of cars, trucks and railway wagons. Just now I showed you the picture. That is a truck. The leaf spring which is used in a truck. Not only in trucks, in addition to the trucks, these springs are used in cars, railway wagons or heavy vehicles like lorries also. So where you can use this one as a suspension system. A multi-leaf spring consists of series of flat plates, usually semi-elliptical in shape. See, if you see the figure here, so yeah, see, it is in the form of a semi-ellipse. The shape of this plate is, so you can draw this one here. It should be something like semi-elliptical shape. So it's not full ellipse. So it is. They are in the shape of a semi-elliptical. You can see this in the figure. They form a semi-elliptical shape. Then the flat plates are called leaves of the spring. So those plates are called as leaves of the spring. The leaves have graduated length. What is the meaning of this one? You can observe that in the figure. The leaves are having graduate length. If you see this picture clearly, see the bottommost plate will have only this much length, and the next plate up to this point, the next plate up to this point here, then like this. See, the length is gradually increasing here. So for each leaf, the length is gradually increasing length. Finally, you have this is the leaf which is having the total length or full length. So these leaves we'll call it as a graduated leaves, and the leaves which are having a total length. So that means from this connection to the connection, this type connection, we'll call it as a full length leaf. So that means you have two types of leaves in this leaf spring. One group of leaves is graduated leaves. That means the length is not equal to the total length of the spring, but the length is gradually increasing for each plate. So those set of leaves, we'll call it as a graduated leaves. Then on the top you have a full length leaves. So that's what the meaning of graduated leaves. The flat plates are called leaves. The leaves have graduated lengths. That means from the bottom to the top leaves, if you take the leaves, their length is increasing gradually. The leaf at the top has the maximum length, and the length gradually decreases from the top leaf to the bottom leaf, or vice versa. So from bottom to top, the length will increase, or from the top to bottom, the length will decrease. The longest leaf at the top is called the master leaf. The longest leaf at the top, we'll call it as a master leaf. So then it is bent at the both ends to form spring eyes, like already told. So you already seen that in the picture. At the end of the top leaf, you have a which is bent in the form of eye, something like this. This eye is connected to the automobile body. Two bolts are inserted to these eyes to fix the leaf spring to the automobile body. So that's what we have already seen it here in this picture. So this is the eye of the spring. So through this eye, it is attached to the automobile body. Okay, right. So you have graduated lengths of leaves. So and also you have a one leaf which is at the top, which is having the largest length. So the top length leaf we call it as master leaf. So then the leaves are held together by means of two U bolts and at a center clip. So that also you can see that in the figure here. This is U bolts. So these are held in position by these two U bolts. These are the two U bolts. Then rebound clips are provided to keep the leaves in alignment and prevent the lateral shifting of the leaves during the operation. So this also already told to you. These are what we'll call it as rebounding clips. This one and this one. Maybe this side also you have two such more rebounding clips. So these are used to keep all these leaves are in aligned position, and at the same time it will prevent the lateral shifting of these leaves one upon the other. So this is about the construction of this leaf spring. Rebound clips are provided to keep leaves in alignment and prevent lateral shifting of the leaves during operation. At the center, the leaf spring is supported on the axle. So that you can see that from the picture, you can clearly see that at the center only it is supported. Leaf springs are provided two extra length leaves in addition to the master leaf. So this is another statement. Just now we see what is master leaf. So master leaf is the topmost leaf which is having the largest length in all the leaves. We call that one as a master leaf. Or this master leaf is, we can also call it as a full length leaf. So in addition to one full length leaf or master leaf, there may be one or two more extra leaves. Extra full length leaves can be used in the spring. So you can see that in the picture also here. See this. This is the one full length leaf, and this is another full length leaf. So you have two here. One extra leaf is there. So that's what he stated in this statement. So in addition to master leaf, there may be one or two extra full length leaves. So in the leaf spring, the purpose of this one is the extra full length leaves are stacked between the master leaf and the graduated length leaves. So these extra full length leaves are provided to support the transverse shear force. This extra full length leaves. So in addition to master leaf, one or two extra full length leaves are provided to the spring such that it can support the shear force. So why we call it as shear force? Like already told. So if I take the half of the force of the spring, so here we can treat that one as a cantilever. Here the load comes on the spring. So that means in the analysis you can treat that leaf spring as a cantilever. So when it is subjected to a force at one free end, so we know this is a free. For this one, we know how to draw the shear force and bending moment diagram. The shear force diagram is going to be something like rectangle here. since your all the leaves are not up to this point, so you have a graduated leaf, something like this. One leaf is up to this point, then next is up to this point, something like this. They are graduated in length. So if you don't have all full length leaves here, since the shear force is same throughout the length, so this cannot carry the required amount of shear force. So that's why 2 more additional full length leaves are provided to the spring to accommodate this transverse shear force. Right? So this is about the construction of the spring, this leaf spring. Okay, now in this diagram also you can clearly see that. See, this is the main leaf or master leaf. We'll call it as the here. This one is the one extra full length leaf. Then remaining thing we'll call it as these leaves. We'll call it as a graduated leaves. 1, 2, 3, 4 graduated leaves are there. One extra full length and one master leaf is there. So now here at the center here it is going to be fixed to this U bolts. So you can see the U bolts or center bolt, you can call it as U bolts. So you can see that U bolts are there. It is connected here. Then these are the rebound clips, or you can call it as a rebound clip, and this is the eye of the spring. So from this, whatever we discussed it, you can see that same thing here in this picture also. Now, since you are connecting to this leaf spring at this to the automobile body through this eyes, the load comes onto the spring at this location as well as at this location. So due to symmetry, I'll take the equal load distribution on this leaves. So here if the leaf load is P, here also it is P. Then since it is fixed here at this location, so if I draw the free body diagram for equilibrium, here the reaction force should be 2P. So, and also if you, while analyzing this, if you see this one here, since we are fixing this one, we'll consider only half of the portion of this leaf spring for the analysis. So this part only, either left portion or right portion, only this portion of the leaf we'll consider for the analysis. So in that case, the load acting on the leaf, we need to take it as P only, and we'll treat this leaf as a cantilever. That means, so we need to treat this one, the leaf spring, as a cantilever which is subjected to point force at the free end, where the total length of the leaf is taken as 2L. So therefore, the length of the cantilever is going to be half of the length. That means this half of the length is going to be only L. So that means in the analysis, you need to consider a cantilever of length L, which is subjected to a point force P. So now, for a cantilever, we know, so this is subjected to shear force and bending moment. So because of shear force, you have a shearing stress, and because of bending moment, you have a bending stress. So if you compare the magnitude of shear stress to the bending stress, it is negligible. That's why we are not interested in finding out what is the magnitude of the shear stress. We will interested only out of finding out the bending stress. So next step is how I can find out the magnitude of bending stress in this leaf stems. So here the difficulty or maybe the problem is there. If all the leaves are having same length, then there is no issue. But here our leaves are gradually increasing from the bottommost one is going to be having the smallest length to topmost is having highest length. So therefore, we need to follow some different criteria to find out what is to find out the bending stress in this leaf. So for that purpose, what we'll do is, these total leaves, whatever may be the total number of leaves are there in the spring, they are divided into two groups. So namely, master leaf along with graduated length leaves forming one group. So that means in those two groups, the one group is the master leaf plus the extra full length leaves. These combined as a group 1, and then remaining graduated lengths. So 1, 2, 3, 4 are there here, 5 are there. These graduated lengths are grouped into another group, that is group 2. So now we'll do the analysis separately, and finally we'll apply some compatibility equation between these two so that we can find the stress in these leaves. So right, okay. So now we'll see the analysis how we can find the stress in these leaves. So remember, for our purpose, we are grouping these total leaves into two groups. One set of leaves is master leaf and extra full length leaves, and then other set is all graduated leaves will take it as another group. So now, then how I can model this one? So because here, first if I take graduated leaves, their length is changing. Their length is not constant here. So length is gradually increasing. So now, if I want to treat that one as a cantilever having equivalent length, and which is subjected to point P. If this is the case, if I know the length is uniform for all the leaves, I can easily calculate the bending stress. So from that, I can easily calculate the bending moment. Bending moment is nothing but P into L. So once I know the bending moment, I can use the bending equation. M by I is equal to sigma by y. So using this equation, I can calculate the bending stress. Sigma is nothing but our bending stress. We can calculate it. The problem is here is if while calculating the I value and also while calculating the here, the length is not same. So you have a difficulty in calculating the I value. So for that, we need to adapt some other approach. How I can model this graduated lengths also leaves having uniform cross section. So for that, I'll go to the next slide. See, okay. So before that, what are various notations we are going to use in the analysis of this leaf swing? Those things we'll see first now. So NF is number of extra full length leaves. That means this includes your master leaf plus extra full length leaves. Where NF consists of number of extra full length leaves. Then number of graduated leaves including master leaf. So here your NG should be number of graduated length leaves including master leaf. So here in NF you have to consider only extra full length leaves. So you have to exclude the master leaf here. Then you have two sets, that is only extra full length leaves one set and number of graduated leaves including master leaf. We consider master leaf is also a graduated leaf, that is another set. So therefore the number of extra full length leaves are denoted by NF and number of graduated leaves is denoted by NG. Then N is the total number of leaves, that is nothing but your NF plus NG. NF plus NG will give you the total number of leaves, that is number of graduated leaves including master leaf plus number of extra full length leaves. Then B is the width of the leaf. You can see that if you go back to that figure, each leaf has a width B. So all are having uniform width only. You can see that here, this is what we'll call it as width. So even though the length is different for all the leaves, but the width is same only. See, you can see that each one is having width is same only. The width of leaf is same. So that width is denoted by small b. So only length is changing, but width remains same for all the leaves. So that then only they can be stacked in using this rebound clips also. Okay, B is going to be the width of the leaf. Then T is the thickness of each leaf. So that also you can see that in that figure. You can see that thickness is also uniform only for all the leaves. So this is the thickness. This is what we call it as for one leaf. This is the thickness. Or else if I go back to this diagram here, so this one is going to be thickness of the leaf for this leaf, for this leaf, for this leaf. We'll assume the thickness is same for all the leaves. This is the thickness. This is the thickness which is going to be same for all the leaves. So then L is the length of the cantilever or half the length of the semi-elliptical spring. That's what I already told to you. So total length will take it as L, but half of the length. So from this point onwards, since we are considering this one as a cantilever, this length should be L. So this is half of the length of the your semi-elliptical shape. So total length is from here to here, which is 2L. So half of this length is going to be L only. Then P is the force applied at the end of the spring in newtons. That's what we already seen. PF is the portion of the P. Here it is capital P. Portion of the P taken by the extra full length leaves. That means for this leaf spring, we are applying a force of capital P. We are applying a force of P here in this amount of P. So since you have two different groups of leaves, one is extra full length, first set is extra full length leaves, other one is graduated leaves. Then what is the in this load P? the load is total load is taken by all these leaves. These leaves will consist of two sets. So therefore, the total load is taken by these leaves. For equilibrium, your total load is your PG plus PF. So PG per PF, where in that this PG is the load taken by these graduated leaves, and PF is the load taken by the extra full length leaves. So this is the equilibrium equation. I am applying a load to all these leaves. So the total load is taken by all these loads. So but in that extra full length leaves is taking a load of PF and graduated load is taking a load of PG. But what is PF? What is PG? That is our next question. Out of P, how much load is taken by the extra full length leaves and how much load is taken by the graduated leaves, that we need to calculate. So that's why we are denoting PF as portion of the P taken by the extra full length leaves. Of course, load is always expressed in newtons. PG is the portion of the P taken by the graduated length leaves. So these are the notations we are follow in case of this leaf springs. NF, total number of extra full length leaves. NG, number of graduated leaves including master leaf. N is total number of leaf, which is nothing but sum of NF and NG. B is the width of the plate, each leaf. T is the thickness of each leaf, and L is the half the length of the semi-elliptical spring, or we'll call it as a length of the cantilever also. Then P is the applied force. In that P, PF is the load taken by the extra full length leaves, and PG is the load taken by the graduated leaves. So now, okay, like I already told, we have two different groups of leaves, and in that also, if you take the graduated length leaves, the length is not constant for all the leaves. So now you can see that here, this is the front view of that leaf spring here. You can see that you have a different lengths. You have a different lengths of leaves for this, something like this. So now, if I have a cantilever, so like we already told, you have to model the spring, half of the spring as a cantilever, which is subjected to a load. Here I am taking the load as PG. So PG is nothing but load taken by this gradual length leaves. So our intention is we want to find out what is the bending stress in this in this graduated length leaves. So for that, we need to model this one as a cantilever. So we have to take it as, we need to find out what is the magnitude of stress in this cantilever, and at the same time, if I want to find out what is the deflection in these leaves, delta. So we want to compute what is sigma B, what is delta. So for that here, if all the leaves are having the same length, then there is no issue. So I can straight away, like I said, we will use this formula M by I is equal to sigma by Y. So if you know what is bending moment, what is moment of inertia, and what is the Y is nothing but half of the thickness, so you can compute the T value. But here, finding out I is going to be difficult thing here, because here the length is going to change from this end to this end. So to model that, what we do is we are making some simplification or some assumptions, and we'll try to model this one as a all these graduated leaves as a one leaf which is having a cross section is something like similar to the triangle. If you see this figure, you can see that here. So by approximating this one as a something like by connecting all the ends of these springs, so we can treat this one as a leaf, a single leaf which is having a cross section of a triangle. So now for triangle we can easily find out what is the moment of inertia. We have a formula. So for that, so you have to construct this one is something like this. So that is what described in these 2 points. The group of graduated length leaves along with the master leaf can be treated as a triangular plate as shown in figure. So then in this case, it is assumed that the individual leaves are separated and the master leaf placed at the center. See how it can be assumed as a triangle. You can see that here in this picture here. Here, the first one is the central leaf. The central leaf is going to be the full length leaf. So that is master leaf. So we group all this graduated length. This graduated length leaves will consist of master leaf also. First, I will place the master leaf at the center. Then I will take the next one, this one. and I'll cut this one into two halves having a thickness of t by 2 and b by 2 and b by 2. I'll place one on the top, one on the bottom. So like this. So that's what I written. The second leaf is cut longitudinally into two halves, each half width b by 2 and placed on side of master leaf. So that means the second leaf is taken and it is cut into two halves along the longitudinal direction, and those two halves are placed one upon the other, one above the master leaf and one below the master leaf. Then the next leaf is also do the same procedure follow for the next leaf, and they place that like this and so on. So for all the leaves the same procedure is followed, so that we get a triangular plate. So you can assume now if you place all these leaves something like this, you can approximate that one as a triangular plate. So similar procedure is repeated for the other leaves also, so that the resultant shape is approximately a triangular plate of thickness T and maximum width at the support as number of graduated leaves into B, because always even though we are cutting it, we are placing it here, it is B by 2, here it is B by 2. So this B by 2 will become only B. So therefore, if I have n number of the ng number of B's are there, the total width is going to be ng into B. So thickness is going to be T. So now once I have a triangular cross section, and if I know the thickness and width, that means those are the cross sectional details, I can find out what is the moment of inertia. Once I know the moment of inertia, I can calculate the bending stress also. The bending stress in the plate is given by, this is the formula just now I told, sigma is equal to m into m by I into y. So bending moment is nothing but the load acting on this graduated leaves. The load acting on the graduated leaves, we are taking it as Pg, and the length of the leaves, length of the master leaf is nothing but L only. So Pg into L is going to be the bending moment. Y is nothing but the maximum thickness. Thickness by 2 is going to be your y. So that is going to be d by 2. And then I is nothing but moment of inertia of your triangular plate. So for the triangular plate, it is going to be 1 by 12 into BD cube. So therefore, that 1 by 12 into B is nothing but ng into B T cube. So now, if you substitute all these parameters, you will get the bending stress. So if I simplify this one further, because here I have T by 2, here T cube is there, and if I bring this 12 to the numerator, if I simplify this, I'll get it as 6 PgL by ng bt square. So this is the magnitude of the bending stress in this leaves, graduated length leaves. But again, I have a formula for bending stress, but still I am not in a position to calculate this because I don't know what is this Pg value. So we are applying a load which is P on the leaf, on the spring, leaf spring, but out of this P, how much load is taken by this graduated leaves, that still it is unknown. Still it is unknown. But only thing is, if I know Pg value, then I can calculate the bending stress. Right? So then once I have the bending stress expression, then I can find out the deflection equation also. The deflection at the load point of triangular plate is given by, so you know, for a cantilever having a rectangular cross section, or for a cantilever, the deflection at the end it is maximum, delta is nothing but PL cube by 3EI. This is the formula from our strength of materials or mechanics of solids. You can say that a cantilever which is subjected to point load at the free end, then the maximum deflection is at the free end only, and it is given by PL cube by 3EI. So the same thing here, I need to apply the same formula. So where I is going to be the moment of inertia, I need to apply. If I substitute that one into here, you are going to get, this is going to be the deflection. Delta Z is going to be the deflection of this graduated length leaves. That is PG L by 2EI max. So which comes out as something like this. If you simplify that, the deflection is going to be 6 PG by E, where E is the Young's modulus, Ng is the number of graduated leaves, B is the width of each leaf, and T is the thickness of each leaf. So don't bother about how we got this derivation, because it is straightforward only. From the strength of materials we have taken that. Maybe in the examination point of view also, they may not ask you to derive this one, but you need to remember this one. I think no need to remember this one also. If you refer your data book, in the data book, these formulas are also available. All these sigma B, delta Z, all these formulas are available in our data book also. So later I'll show it to you those formulas also, right? So this is how we can model the graduated leaves. So by modeling the graduated leaves as a something similar to an equivalent triangular plate, we can find the bending stress and we can find out the maximum deflection in the leaves. So, but still we don't know. We have an expression for bending stress, but still we don't know what is the magnitude of the load Pg which is acting on these leaves. If I know Pg, then only I can calculate the bending stress. Even deflection also I am able to calculate that. So then to calculate this Pg, now we need to model the full length leaves, extra full length leaves also, and then we need to apply some compatibility equation, so that from that we'll get this Pg and PF values. So once you have PG and PF, then you can calculate what is the bending stress in graduate leaves as well as full length leaves. So now coming to the modeling of extra full length leaves. So here you have two extra full length leaves. Those can be modeled as something similar to what we did in case of graduate leaves. But here they are having same equal length. Extra full length leaves means all the leaves will have same length here. So if I have two leaves, then I'll take the second leaf, I'll cut and I'll place one upon the other, something like this I'll get. So then this is going to be the modeling of this extra full length leaves. It is a straightforward equation only. So you can straight away write the expression for the bending stress as well as deflection. Extra full length leaves can be treated as a rectangular plate of thickness T with uniform width NF into B as shown in this figure. NF into B is nothing but the total weight, and here length is going to be L and thickness is going to be T. So then bending stress is nothing but same formula here, MB into Y by I. So MB is nothing but the load acting on this extra full length leaves, we'll take it as PF. PF into L is going to be the bending moment into T by 2. T by 2 is going to be the half of the thickness of the leaf. So where you have the maximum distance from the neutral axis. And then for a rectangular cross section, I is going to be BT cube by 12. So that's what we are taken here, BT cube by 12. So then you got the expression for the bending stress. If you simplify this, you get 16 PF into L by NF BT square. So similarly, we can find out the deflection also. Deflection is nothing but, like I told, the formula is PL cube by 3I. PL cube by 3I. Here PI is nothing but PF. L cube by 3E into I is nothing but this value. So now I have expressions for bending stress in graduate length leaves as well as extra full length leaves. I know the expression for the delta G and delta F. Those are deflections in extra full length leaves and graduated leaves. Now the question is how I can find out the magnitude of PF and PG. That is the thing here. So to find that, what we need to do is we need to use the compatibility equation. Compatibility equation is nothing but the relation between deflections of these two leaves. So you have one group which is extra full length leaves, the other group is graduated leaves. So if you look at the diagram here, all these leaves are, so even though for the purpose of analysis, we divided them into two groups, but here all are staggered together only. So for the purpose of analysis only, we divided them into two groups, but here all are staggered together. That means whatever may be the deflection of this leaf, it is same for this leaf also. That means all the leaves should have same deflection only, because they connected here, they firmly connected to each other. Whatever may be the deflection of this graduated leaves, that should be equal to the deflection of your full length leaves. That is what your compatibility equation. So we have expressions for deflection of graduated leaves, and we have an expression for deflection for full length leaves. So here this expression should be same as your expression for the deflection of a graduated leaves. So now from that you can clearly see that since deflection of full length leaves is equal to the deflection of the graduated length leaves, our delta G should be equal to delta F. So now if I equate that, I'll get one more equation. So earlier I written the equilibrium equation. Your total applied load P should be equal to PF plus PC. So this is one equation. Then if I equate the deflection of graduated length leaves to the equation of full length deflection of full length leaves, I'll get one more equation. Then two equations and two unknowns. I can solve for PF and PG. Once I have PF and PG, I'll take those values, I'll substitute here into the expression for stress and deflection. I can calculate both stresses as well as deflection in extra and full length leaves. So for that, so what we need to do is we need to equate these two deflections. So this is the deflection of graduated length leaves, expression for the graduated leaves, and this is the deflection of extra full length leaves. Then by equating this, so I can cancel out the similar terms. EBB cancel out, BB cancel out, T cube will cancel out, L cube will cancel out. Then from this, I can write a relation between PG and PF. So that is going to be, if you simplify this, PG by PF is nothing but 4 by 6. You are going to get 4 by 6 into NG by NF, or else it is 2NG by 3NF. So that means we have a relation between PG and PF. So this is the second equation what we got. First equation is, like already told, this is our first equation. So then this is the second equation. Then using these two equations, I can solve for PG and PF. So if this is the second equation, then if I substitute into that and if I simplify that, I'll get PF is equal to 3NF into P by 3NF plus 2NG, and PG as 2NG into P by 3NF plus 2NG. So that means now if I know capital P and if I know number of extra full length leaves and number of graduate leaves, I can calculate what is the load taken by this extra full length leaves, and I can calculate load taken by the graduate leaves also. Once I know this PG and PF value, then you can compute the stresses as well as deflections also. So now if I come to the stress portion, so now if I want to compute what is the stress in the graduated leaves, so then earlier whatever deflection or whatever stress equation I derived for the graduated leaves, here this one 6 PG L by NG BT square. In this PG, I'll substitute this expression. I'll substitute PG in terms of P. So just now we got it, PG is equal to this one. If I substitute that PG expression in that equation, I'll get the bending stress in graduated leaves as 12 PL divided by 3NF plus 2NG into BT square. And similarly, you will get the stress in the extra full length leaves as 18 PL by 3NF plus 2NG into BT square. So these are the magnitude of the stresses in magnitude of bending stresses in graduated leaves and full length leaves. Now if you carefully observe these two expressions here, the denominator is same for both the things. You can see that 3NF plus 2G into BT square here also the same thing. 3NF plus 2NG BT square. Denominator is same. Even in numerator also it is PL and PL. Only thing is here this constant value here it is 18. So that means which one is having a more stress? Even though we are applying a force P, the stress in the extra full length leaves is more than the stress in the graduated leaves. Why? Because here you can see that here it is 18. Or else if I write an expression for sigma B of extra full length leaves divided by sigma B of graduated leaves. If I take a ratio of these two stresses, so what I get 18 by 12 I get 18 divided by this PL by this thing, this one, and this PL by this denominator will cancel out each other. We are going to get only 18 by 12, which is nothing but 1.5. 18 by 12 is nothing but 1.5. That means your stress in the extra full length leaves is 1.5 times stress in graduated leaves. So that means the stress in the extra full length leaves is more or 50% more. 1.5 means it is 50% more than this graduated leaves. So that's what I said here. It is seen from the above equations. The bending stresses in full length leaves are 50% more than in graduated leaves. So but here this is not the proper way of designing the spring, because if you design, you are using the same material for all the leaves, but you are getting a maximum stress in one set of leaves and compared to the other set of leaves. So therefore what we need to do is we need to make sure that the stress in this extra full length leaves as well as the graduated leaves should be same. Sigma B F should be equal to sigma GF. So sigma B into G. So that means if the stress in all the leaves is same, then only we can say that that is the good design or optimum design. But with this analysis, what we are getting is, we are getting that the stress in the extra full length leaves is 50% more than the stress in the graduated leaves. So now there should be some mechanism, some adjusting mechanism or load distribution mechanism, or the load distribution mechanism need to be changed in all these leaves such that will make the stress in both group of the leaves is same. That process what we call it as the nipping of a leaf spring. That what we call it as equalizing the stresses in both graduated leaves as well as extra full length leaves. That process what we call it as nipping. So we'll see what is the nipping also here. So one of the methods in equalizing the stresses in different leaves is to pre-stress the spring. So that means before putting to application, if the spring is under stress, then that is what we call it as a pre-stress. Pre-stress means before putting into the application, that means before assembly that leaf spring into the automobile body, the spring is still in the some startup stresses are developed in the spring. That those stresses we call it as a pre-stress. So if I am able to develop the pre-stresses in the spring such that when it is put it into the load, then it will nullify the some portion of the load effect. So therefore the stresses are equal in both kinds of stresses. So then that process what we'll call it as a pre-stressing of the spring, or we'll call it as a nipping also. Why it is called nipping, we'll see that. The pre-stressing is achieved by bending the leaves to different radii of curvature before they assembled with the center clip. So that's why you can see it here. Earlier diagram, if you see the what I have shown, that picture of the leaf spring, that is after assembly of all these leaves. But before assembling of the leaves, if you construct the spring such that here, if you have a large radius of curvature for the full length leaves and small radius of curves for a graduated leaves. So you can see that here, this is a graduated leaf and this is a full length leaf. So now you can see that the radius of curvature is different. So they are not bent to the same radius of curvature. Here for this it is R1, for this is R2. Your R1 is more than R2. So that's why they are bending into different radii of curvature before assembly. So therefore, because of this, there is a gap between these two leaves. There is a gap between these two leaves. This gap is nothing but what we'll call it as a nip, which is denoted by C. This gap we'll call it as a nip. So that's why this process is calling nipping. That means before assembly, we'll keep some gap between these graduated leaves and full length leaves, and then we'll forcefully assemble such that these leaves, so these two will come in contact with these two each other. So that means this gap can be closed after assembly. So you can see that I have shown a picture to you where in that assembly there won't be any gap in the leaves. So only this is the process which is employed before assembly. So by doing so, some sort of pre-stresses will develop in the springs, which will make sure that the stresses in both the leaves is going to be same. As shown in figure, full length leaves is given a greater radius of curvature than the adjacent leaf. The radius of curvature decreases with the shorter leaves. You can see that in this picture. The initial gap C between the extra full length leaf and the graduated length leaves before assembly is called the nip. This gap what we can call it as the nip, or we'll call it as the initial gap between the extra full length leaf and the graduated length leaf before assembly. Say make sure that after assembly there won't be any gap or any nip in the leaf spring. Such pre-stressing achieved by difference of radii of curvature is known as nipping. Nipping is the common in automobile suspension springs because by this process they will equalize the magnitude of stresses in all the leaves. Okay. So now, if you make that is nipping is, then what is the magnitude of stress then? That means through this nipping process we are pre-stressing the springs. So therefore, such that we are pre-stressing the springs such that the magnitude of stress in the graduated leaves is equal to the magnitude of stress in the full length leaves. So therefore, what then? That means we are modifying the stress. Then what is again after nipping process? What is the stress in these springs? So we want to calculate that also. Again, for that, we'll use the compatibility equations to derive that. So, before, if you don't follow the nipping process here, this is the magnitude of the stress in the graduated length leaves. So then, after and this is the magnitude of stress in the full length leaves. So then, since we are equalizing this, so from this what you will get is, you will get a relation between Pg by Pf differently, Ng by Nf. Why it is Ng by Nf? Because earlier the load distribution is different, now the load distribution is different. See, earlier you got some other ratio, here you got 2 Ng by 3 Nf. Now, because of free stressing here, the stresses are equal now. Earlier they are not equal, now they become equal. So when they are equal, then you get Pg by Pf is nothing but your Ng by Nf. So then, using the another equilibrium equation, that is Pg plus Pf is equal to P, you can calculate the expression for Pg and Pf. Pg is going to be Ng into P by N, where N is the total number of leaves. That's what we already taken. That is nothing but the summation of Ng and Nf. So it is a straightforward Ng into P by N and Nf into P by N is going to be the load taken by the graduated leaves and full length leaves after nipping process, or due to nipping process, the load distribution is changed now compared to the earlier one. So once this is the case, then we'll use the same deflection equations where we used what we derived earlier, and we'll use the same stress equations also, then so that we can find out what is the magnitude of the stress in this and deflection in these leaves also. So first, if I take the expression for this is the delta G. So 6 Pg L cube by E Ng into Bt cube. This is what we already seen in the previous case. So the deflection expression remains same. Only thing is the magnitude of Pg is going to be changed now. So now if I substitute this Pg as Ng into P divided by N, this is the expression for okay. So if you substitute that, you will get the expression for delta G. Even you will get the expression for delta F. But here this delta G and delta F, before assembly they are not same. Before assembly there is a gap between delta Z and delta F. That gap is nothing but your C. That is nipping or amount of nip. We will call it as C. So this delta Z minus delta F should be equal to your C. So therefore, under maximum force, the deflection of graduated leaves will exceed the deflection of extra full length leaves by an amount equal to initial gap or initial nip C. So that means this is the compatibility equation we need to use. So with this compatibility equation, so your C is equal to the difference in those two deflections here. So now if I substitute for Pg and Pf, just now what we derived here, this is the expression for Pg and Pf. If you substitute those expressions into this, you are going to get is 2P L cube by En into Bt cube. So that means this is the expression for the nip. That means in order to equalize the stresses in extra full length leaves and graduated leaves, how much initial nip you need to provide to the spring. So to calculate that, you need to use this expression. Anyway, these expressions are all, everything is there in the data book. That's why I'm not deriving all these things. Okay? Alright. So once you know this one C value, then you can calculate the initial preload also. That means, see, we are taking the leaves something like this. One is having a larger curvature, or okay, I'll go to the next previous figure here. Here we are taking something like this before assembly. So now we need to pre-stress these two leaves such that they come close to each other, such that the C will become 0. So now to do that, how much preload Pi I need to apply for this one, these two leaves. So that is what we call it as a Pi. Pi is nothing but the preload. If I want to calculate the magnitude of how much preload is required for making that gap is 0. So the initial preload Pi required to close the gap C between the extra full length leaves and graduated leaves is determined by considering initial deflection of the leaves. So now we already calculated the C value. That C is nothing but the initial gap delta G of I plus delta G of F. So from that, this C is nothing but just now we got it as an expression as 2PL cube by En into Bt cube, and then delta G expression, we know the expression for delta G. So in that we need to substitute what is Pi. So we are applying only initial preload. Our interest is we want to calculate what is the initial preload. Wherever P is there, Pg or Pf is there. In this Pg and Pf, you need to substitute Pi by 2 and Pi by 2. Then From this, you can get an expression for your initial preload. That is Pi, which is 2ng nf into B divided by n into 3nf into 2ng. So that means now I'm able to calculate all the parameters. So that means what is the initial gap between these two leaves I need to provide, that is nothing but C, so that or such that the magnitude of the stress in all the leaves is same. So I have an expression for C, and then in order to create this C of how much preload I need to apply these two springs such that this gap can be closed, that is nothing but your initial load or initial preload. So that preload expression is this. So these two expressions are available in the data book also. You can pick straight away. You can pick from that one from the data book. Only thing is you should know what is C, what is initial load. Then once you've done that, then if I want to calculate the stress in the leaves, so then see we are pre-stressing it. That means you need to remove that whatever may be the magnitude of load that comes on the full length leaves. So because of the free stress, you are creating a negative stress in the leaves such that it will be the stress is equal to the graduated length leaves. So therefore, PF minus whatever may be the preload, we need to subtract that Pi from this. So from that, we'll get our expression for the sigma B. So that comes out as 6PL by NBT square. The same thing can be applied to the graduated length also. This is also equal to your bending stress in graduated leaves. Sigma B in G also, graduated leaves also. That's why it is same. So it is same for both graduated leaves as well as extra full length leaves, which is going to be 6PL by NBT square. So see here, this is different. This expression is different. Earlier expression is different. See here, this is same for both extra full length leaves as well as graduated leaves when nipping process is used. Without nipping, your stress values are different. So these are the stress values. The stress is different in both the leaves. This is the expression for the graduated leaves and this is the expression for the full length leaves. The expressions are different. So therefore, after nipping process only, you are getting the equal stress values in all the leaves. So and the magnitude is given by this one. Similarly, if you want, you can calculate the delta also. You can calculate the delta also, which is going to be same for all the leaves also. Even that expression is also available in the data book. So I'm not getting, okay, so it is already now 10:30. Maybe I'll stop at this point. So I went through quickly because you are not available for the remaining classes. So I want to complete it very fastly. So maybe it may be speedy for you, but try to understand it. And if you have any difficulty or any doubt, you can post in the classroom. We'll discuss your doubts also. So then, if required, I'll share this PPT to you so that you can go through this PPT also. After that, only theoretical discussion is over. We left with only some numerical problems, solving some numerical problems. If time is there, we'll take up that in the next class. Otherwise, if you have examination, maybe I don't know whether you are available for that. If you say some free time, then we'll discuss these problems in that free time also. Okay, anyway, I'll close today now at this point. Maybe we'll continue in the next class if available. Okay, right. I'm closing it now.
Okay, sir.
Right. So I think I already placed